Hello everyone, my name is Alexis and I'm going to present you our work on the transfer matrix method applied to anti-reflective coating rendering. So our motivation was to model thin film coating. What is a thin film? A thin film is a thin layer of a material that you apply on top of another in order to modify its transmission and reflection properties. Let's take an example. A bubble. A bubble is a thin layer of soap between two layers of air. And this thin layer of soap modifies the reflection and transmission properties of the air, and that's why we're able to see those nice iridescence effects. Thin film coatings are often used for manufactured products. For example, lenses in this camera right here. We apply anti-reflective coating to lenses in order to maximize the amount of light that is transmitted through the lens and minimize the light that is reflected, because the reflection is the source of stray light. Same thing goes for solar panels. For solar panels, we use coatings in order to maximize the light that is transmitted through the panel to the photovoltaic cell and to minimize the amount of light that is reflected because it's loss of energy. So what are the current solutions to model those thin films? Well, for one layer, Belcour and Al offer a very nice spectral integration in order to be able to render one layer thin films in real time. For multiple layers, there are two main works, one by Hirayama and Al, which use the Airy summation, which is a bit cumbersome to use, and they make several simplifications that we don't make. And Ikar and Al derive a full BRDF model for a stack of thin films by solving the Fresnel diffraction equation in those thin films. Our solution used the transfer matrix method, which is a method used in optics. It is applicable to multiple layer coatings. It is very easy to use because it only involves 2x2 matrices compared to the cumbersome Airy summation. We don't make any simplification, especially the Stokes reversibility simplification, which we're going to look at slide 15. And our method can be used with any BRDF model because we only derived a new Fresnel coefficient, so you can use it with any reflection model you may use. So why apply it to anti-reflective coating? Well, anti-reflective coating is very important to be simulated efficiently and accurately because they are widely used in the industry on top of manufactured material. So it's important to have a simple way to model them. And it's also a good example where multiple layers are necessary. On the graph right here, you see the reflection in energy for an air glass interface at normal incidence. In blue right here, when there is no coating, you have about a 4% reflection. When you use one layer, you can go down to about 2%. But if you want to have a highly efficient anti-reflective coating, you need to add more layers than that. And about 4 layers right here, you can see that you're almost at 0% over the full visible spectrum. So let's describe our problem. We have a material that we call substrate, on top of which we add a coating. The coating is parallel to the material, and this coating is made of several layers, each layer parallel to one another, each described by a thickness and an index of refraction. What is happening when there is no coating? Well, light is reflected on top of our material following the bidirectional reflection distribution function, the BRDF, which we have an example right here for a microfacet model. It involves three terms, D, G, and F. D and G depends on the geometry of the material, and F is a Fresnel term, which describes the amount of light that is reflected in the direction W0. We often use an approximation called the Schlick approximation in order to model our, our Fresnel term right here, which depends on the direction the light is reflected in and the index of refraction of materials. So now what happens when we use thin film coating? Well, the geometry doesn't change, so D and G stays the same. But what about? Well, when we use a coating, there is a new phenomena that appears that is called interference. So in order to model this interference, we can't simply consider light as a ray anymore. We can't just add intensities. We need to track the amplitude and the phase of the light as a wave, and this in order to derive a new Fresnel term. And in order to derive this new Fresnel term, we're using the transfer matrix method. So we consider light as a wave. Light as a wave is described by an amplitude and by a phase that is in the exponential right here. K is a wave vector, which is defined by 2 pi over lambda. Lambda is a wavelength of our wave. And in the index of refraction of the medium the light is propagating through, and u is the direction of the wave. And our transfer matrix method, we need to track two things. It tracks the modification introduced during the propagation in each layer, and we need to track the modification introduced at the interface between the layers. So let's start with what's happening during the propagation inside the layer. Well, we have light that comes to our coating that is immediately reflected in the direction W0 that we can represent here, where here is the point in time where the light is reflected. But another part of the light is transmitted through the coating, is reflected on our material, is propagating back into the coating and back into the first medium in the same direction W0. But because it has to travel through the coating back and forth, there is a slight delay which induces a translation to the right of our curve right here. This is due to the amount of time the light needs to propagate through our coating. And so now, as you can see, the minimum of our first wave happens when the maximum of our second wave happens. So if we sum those two waves, they cancel out. And this phenomena is called destructive interference. So now let's see what happens with the thickness. Well, if we increase the thickness, the same thing happens. We have a first wave that is immediately reflected, and we have a second wave that hits through the coating back and forth and back in the same direction in our first medium. But because the coating is thicker, the delay, so the time to travel through the coating increase. So the translation of our curve to the right increased as well. Now, as you can see, the maximum of our two waves are now happening at the same time. So when we sum them, we have a new wave that is double the amplitude of the two waves that we have before. And this is called constructive interference. So now, in order to model that, let's see a bit closer what's happening in the interface right here. So we can say we have three waves. One E0 that is propagating forward just before the interface. We have a second wave E prime 1 that is the wave inside the first layer right after the interface. And we have another wave E1 that is the wave that after propagation inside our first layer. So if we write down our wave, we have E0, which is equal to an amplitude and a phase, K0. So if we write down in our basis X and Z right here, K0, we have this expression right here, which depends on the index of refraction and the angle of incidence of our light. Now, if we write what's happening to the wave inside our first layer, we have the same thing, an amplitude coefficient and a phase right here. But now, if we use our Snell refraction law, we know that we have n1 sinus theta 1 equal n2 sinus theta 2. And the same thing if we multiply by x right here. And so what does that mean? That means that those two terms right here are equal. And if they are equal, that means that the propagation along the x-axis is not going to induce any change in phase. So that means we can only concentrate on what's going to happen on the z-axis right here and ignore what's going to happen on the x-axis. So if we try to write down what's happening, we see that between E0 and E1, we have the interface right here, which we describe for now as an operation called D01. And between E prime 1 and E1, what is happening is we just have the propagation of the wave. So we ignore the x-axis, so only the z-axis. It travels on a distance d1. And if we write down this quantity right here, delta 1, we can write down E0 equals du. So our operation that translates what's happening at the interface time a delay right here times d1. So now that we have expressed what's happening during the propagation, let's try to see what's happening at the interface. So for that, let's have a more detailed drawing of what's happening. So in each layer, we have two waves that are propagating, one that is propagating forward, one that is propagating backward. Each layer is described by an index of refraction n and a thickness d. And at the interface between each layer, we have two coefficients, one that a transmission coefficient, one is a reflection coefficient in amplitudes, and those coefficient depends whether the light is propagated forward or backward. So now let's try to see what's happening at the interface between the second and the third layer. For that, let's express E2 plus in terms of the wave in the third layer and E2 minus. Well, E2 plus is equal to E3 plus that is transmitted at this interface using P32 plus the E2 minus that is reflected at the interface using this coefficient. And now let's express E2 minus. Well, E2 minus is not so easy to express straight away, so let's start with E3 minus. So E3 minus is equal to E2 minus that is transmitted through this interface and E3 plus that is reflected. So now that we have those equations, we can extract E2 minus, and if you write that as a matrix form, we have the relation right here. So let's take some time to analyze what's happening here. So we have those two terms right here, R23 and minus R32, which for a perfect interface are equal. And for this difference right here, for a perfect interface, this difference is equal to 1. And this is what we call the Stokes reversibility simplification. But in real life, nothing is perfect. The interface can have some default, it can have some roughness. So as a general expression, we don't assume that those terms are equal and this is equal to 1. But using the transfer matrix method, we have a simple enough relationship just using 2x2 matrices to be able to keep this form without using any simplification. So now let's see what happens if we combine the interface and propagation. Well, we derived this expression using what's happening during the propagation, and now we know what our D23 is equal to. So we can actually write what is happening, the relationship between the wave in the layer 2 and the layer 3. So our delay here becomes a matrix because now we not only have one wave, we have two waves, one propagating forward, one propagating backward. So it becomes a matrix right here. And it's only a multiplication of 2x2 matrix, which we write in the following way. So D23 times P3. And P3 is a diagonal matrix right here. So now if we combine all the layers, well, we have first wave that is propagating in our first medium that is hitting the first layer of our coating. So it's first hitting the interface and propagates through the first layer. So we multiply that by D01 P1. Then the wave hits the second layer. So first the interface between the first and second layers, then propagates through the second layer. So D12 P2, etc., etc., till it reaches the last thin film layer, which is propagated through, so Pn minus 1. And finally, the interface between the last thin film layer and the substrate, Dn minus 1n. And this is a wave in our substrate. This expression right here only involves a multiplication of 2x2 matrices. So we can write that as a general form in a global 2x2 matrix. And now if we want to express the reflection and transmission coefficient, so first we use the amplitude reflection and amplitude transmission, which are equal to the ratio of E0 plus over E0 minus, and here E and minus over E0 minus. What can be noted here is that we assume that En plus is equal to 0. That translates to that we assume that there is no light, no source of light coming from under our substrate. So in general case, it's not true. But what's happening is that if we have a second source of light under the substrate, it's not going to make any interference with our first source of light. So what we can do is we can treat those two lights separately because they're not going to interfere with one another, and then we can just add up the energy coefficient we're going to obtain for those two sources of light. And finally, using those amplitude coefficient, we have our energy coefficient right here, Be careful using those formula because it depends on the polarization of the light, but as general, it has this global shape. So now let's see our results. Uh, so the first question we can wonder is how many layers for an efficient anti-reflection coating? Well, if we represent the energy reflected as compared to the number of layers of our coating, we see that as we increase the number of layers, the energy decrease and is more flat over the full visible spectrum. And once we reach 4, and when we go to up to 5, the we see that the reflection start to increase a little bit, even if it's flats out on the extreme border of our visible spectrum. So we want to compare what's happening with a 4 and 5 layer, and we see those small oscillations right here. And so we were starting to wonder if the spectral integration would be important for our highly efficient anti-reflective coating. So if we compare what's happening with no coating and with one layer, we see we have a decrease of the reflection energy and as well as an increase of the light of the time to compute. And if we go up to 4 layers, we see that we have a dramatic increase between 1 and 4, but also an increase of time. So the time is increased linearly with the number of layers. And if we go up to 5 layers, we see that the time increase, but the difference is not so much noticeable. And so we decided to just use our full layer coding, which was the best ratio between our performance of our anti-reflection and our time to render. So now if we try to compare what's happening between the spectral and the RGB rendering for our full layer coding, we see the spectral and the RGB are not very different with the eye, and if we plot the difference, the images, we see that most of the difference is due to the noise in the background. And here is a nice illustration of our coding used on the windshield and the windows of the car. So here you couldn't see if there was any driver. Here you could clearly see there's no driver. And we made our code available online using an observable notebook right here. So by default, it's defaulted to a one layer anti-reflected configuration right here. The user interface only have one layer, of course, at the time of the recording, but we're going to correct that so you can change the index of refraction and the thickness for as many layers as you want. Of course, our transfer matrix method can be not only used for anti-reflective coating, but also to observe nice iridescence effect right here. So as you can see, you can also change the model and you can rotate, you can zoom. And the full code is available online in GLSL for real-time rendering. I really like the Lucy model, which highlights the colors very well. So this is available for everyone to use and to enjoy. Thank you very much for listening. If you have any question, I'll be here to answer them. Thanks again, and see you soon.